Dos. Sí, uno, dos. Dos.
Are you already recording? Are you okay? Okay. So I think I went very fast with my previous talk, but I think also because it was very easy, just nice pictures of Alma, and that's it. But oh, yeah. This one, I would like to ask you if I go too fast, you should please tell me to slow down and ask me questions or because yeah, this is the basics that you will need to understand what are we doing with an interferometer. I'll do my best to to give you an intuitive idea on what are we measuring with an interferometer. But that, so if you don't understand something, just stop me and we can try to find another way to explain things, or if I talk too fast as well. Okay, so I showed you in the first part of this morning that there are several techniques to observe in radio, and one of them is to use an interferometer. So an interferometer, with an interferometer, you combine the signal that is coming from different antennas, more than one. You can have an interferometer of two. And for that, you would need to understand a bit how Fourier transform works. Just a bit. It's not that we are going to go deeply into the maths. I understood that most of you have already seen waves, Fourier transform, and all that. So that's why I ask you to stop me if there is something that you just don't know because you have never seen before, or okay? So in this part of the lecture, I would like to, as I said, to a brief introduction, intuitive introduction, how interferometry works, some basics of Fourier transform that we will need to understand what's happening in the images when we go to the lab. And actually, there is a software package that we will be using tomorrow to better understand all of this. And the one that I would like to use is called AppSynSim, Aperture Synthesis Simulator. You will use it in the lab. And there is another one which is called Pinterferometer, which is also quite cool because you can take pictures of yourself and then make that picture go through an interferometer, and then you see what's coming out. So AppSynSim has also, you can also put pictures, but the other one has the webcam option, which is always fun. But I don't know which one will, so I would like to have installed AppSynSim, and perhaps we can try also and manage to install Pinterferometer, but otherwise you guys in your computers can just easily install them. They are Python scripts, so you should be able to download them and play with them as much as you like. I couldn't update the links in this slide because the NRIO website was down during this weekend for updates or something, but I will put the final. It's just the same links I provided before, but with the particular lectures that focus on the interferometry. I will update it, and when I deliver the slides, you will have them there. And very important is that in previous editions of this program, there were two members of Leiden staff that were here and gave a course in interferometry, so they also give good explanations of Fourier transform, so you can look at them. I don't know if you attended to previous editions. You said yes. Okay. So if I have a question, I will ask you. Okay. So the following slides, I didn't make them myself. I grabbed them from Neil Jackson from Manchester, which I think they show very nicely how an interferometer works. And so, yeah, I think all the merit goes for Neil, which is a master of VLBI, by the way. So why do we need a lot of resolution? Why do we need, it looks like we always want to observe to better and better resolution, slower and slower scales, smaller and smaller scales. Why do we need to go so deep? Okay, so this here, Neil prepared this rule where you have the different, what is the, okay. So this is degree size, 10 minutes, 1 minute, 1 arc second, 1 milliarc second, a 100th part of milliarc second. So here you have what are the typical scales of the things, of the objects that we look in the sky, how big they are, right? So you have, for instance, a galaxy cluster would be that scale. Of course, the farther you go in redshift, the smaller they get. But okay, it's just to have a gross idea on how big are things out there. This would be the size of a galaxy like our own. You know, the Milky Way has about, the disk is about 8 kiloparsec large. So if you put that galaxy at a redshift of 1, you would like to observe something which is 1 arc second, which is already small. That would be also the size of a typical AGN not too far away from us. Then if you go to smaller scales, you will have the angular size of Betelgeuse, one of the brightest stars in the sky. But of course, we want to go farther. So what is the typical size of an exoplanet? So we are already in the milliarд second regime. This is very small. So you really need very big collecting areas, a lot of resolution to be able to do this kind of science. And if you want to even go farther, like the Schwarzschild radius of a black hole of a nearby AGN, you are here. So you really need, oh, what happened? A lot of resolution to be able to resolve those objects. I'm trying to speak more slowly. Have you noticed? Okay. Okay. So yeah, what is stopping us? What is the limit? Sorry.
Quick question. What does BLR stand for? Size of BLR?
Blazar, maybe? It's not. They are not. But I think it's a blazar.
Blazar.
Yeah. Of a nearby AGN. We can look. We can ask Neil, but I think that's what he meant. Okay. So, what is stopping us when we have an antenna? What is the resolution that we can achieve with a single antenna? What is stopping us in terms of resolution? So the maximum resolution that we can achieve with an antenna depends on the wavelength and on the diameter of the antenna. Okay, and it has like this. It's proportional to the wavelength over the diameter. For example, in this millimeter regime, if we want a resolution of 1 arc second, of a tenth of an arc second, that would require a dish of 2,500 meters. So good luck with that. So we need to find a way to observe small scales, but not constructing telescopes that are so big, right? Okay, so here now there is a plot of the things that can be resolved with single dishes from Earth, right? So, okay, so the resolution of the eye would be around this. This is the C limit of a ground-based telescope. This is the HST, and this is the BLT. I guess you guys know a bit this. Okay. And in radio, this is the Jodrell-Bank single dish at 5 gigahertz. So Jodrell-Bank could be in this regime. So clearly, we cannot reach any of those structures with a single telescope. So what do? Okay, yeah, this is a graphical nice plot that I grabbed from Lisa's talk. Yeah, so this is to show you the limit of a single antenna. So what we can do is to try to combine more than one antenna. And then in that case, if we add more antennas in the game, our resolution limit will be determined by the distance in between our antennas. Okay? So when we are working with an interferometer, now the resolution comes determined by the distance of the antenna. So the maximum distance in between the antennas of an interferometer will give us the resolution. Okay? So if we add the technique of interferometry and then we spread antennas far away, then we can go and study this object, right? So this is, for instance, the resolution that would have the BLA interferometer at 5 gigahertz. So you are already here. Merlin is a combination of arrays, of antennas as well at 5 gigahertz. ALMA can reach this regime. It's quite impressive. This is the global VLBI, the network that I showed you before. And this would be a space VLBI, like with also using satellites. And yeah, of course, the interferometer technique is also being applied in the optical wavelengths. So you have, they also try to use the interferometry to break the limit of in the resolution. So yeah, actually, we jumped from the case in which radio was the worst case to study small objects, because we were limited by the size of the antenna, and because the wavelength is larger. So because the resolution is proportional to lambda over d, yeah, the larger the wavelength, the worse resolution you will get. But now happens that with the help of interferometry, now the best resolutions can be achieved with radio. So the records of resolution come from radio observations with interferometers. Okay, so I will try to give you an intuitive idea of how an interferometer works. I hope I can manage. Okay, so perhaps you have already seen a bit of interferometry in your courses. Yes, no? Some of them? Okay. So this is another way of visualize this Young's experiment that he did in the 19th century. So we will think of a point source here, and then we will let the waves go through two small holes here, okay? So then the waves will go through this through these holes, and then we will see the result, what comes out on the other side. So because the waves go through these two holes, there will be an interference of these waves. And depending how they add up, you will see the result on the other side. Okay, so again, it's equivalent to what I was trying to tell you before. Your resolution is proportional to lambda over d, where d is the separation of in between the two slits. Okay, well, this was the case of a point source. Let's make this source a bit larger. So imagine that instead of having a point source, now the source, it's a bit larger. So what could be the result on the other side? So here, I hope you can see the colors well. Okay, so the original point source here would have, as a result, the red wave on that side, and then the side, cyan, whatever, light blue, will have the light blue on the other side. So as the waves go through, they start to add up with interference, and the final result, you can see here, they start a destructive addition. So then the final result has a much lower amplitude than initially was. Okay. So as you make the source larger, the result, the final wave becomes weaker and weaker. So let's make this source even much bigger. Let's make this source as big as lambda over d. The result on the other side is a totally flat wave. So if we have a source the size lambda over d, we cannot measure at the other side, right? It's totally gone.
We get nothing.
We get nothing. Yeah, that's because they add up. They start, so they go through one of the holes, the other. They add up when they go through, they add up destructively, and we get nothing. So with this separation, we are only able to detect sources that are smaller than lambda over d. And now we can make the source even larger. We will not be able to detect anything on the other side. So we are losing the spatial information that is larger than lambda over d. We are just sensitive to smaller scales. That's how it works. Okay. Yeah, we can. Instead of, so in this case, we had a source which is size lambda over d, and we see that on the other side we get nothing. What happens if we still keep the same source size, but now we move these two slits a bit closer, right? So now we will be able to detect, again, larger sources. So the same source that in the previous case was not detected on the other side, now we still see something, right? So the distance in between the two slits determines the sources that we will go through. The smaller the distance in the two slits, the larger the sources we will be able to see. That's, yeah, the kind of focus I was trying to explain you before with the ALMA array, okay? The farthest away are the interferometers. The smaller sources we will be able to detect, and the other way around. So, you are familiar with Fourier transform and signal processing. Basically, this is a filter, right? We are doing, to our signal, we are applying a filter. We are just discarding some information from the original source, making it go through a filter, and having this at the other side. So sorry for the resolution, perhaps you cannot see it, but this is just to graphically explain this response of the interferometer to the source size, depending on the distance. So you know that with Fourier transform, we usually talk about a signal in the time space. We do the Fourier transform and we move to frequency space, right? So we have these pairs, time and frequency. In this case, the Fourier transform, we interpret it as geometrically. On one side, we have the source size. So we are moving, our x-axis will be the source size, and its pair, it's the distance in between the two slits. So instead of having time and frequency, we have what we call, so the space, the source size. And on the other hand, we have the UV distance, the U distance, which is the baseline distance, the distance in between the two interferometers. So these are Fourier conjugates. And this is that would be the Fourier transform. Yeah. You will see more examples later. But basically, it's just to give you an idea that this is we are going to work in Fourier space. So instead of working in the source axis, we will be working in the axis will be the distance in between our two interferometers. This is what we can measure from Earth, and this is what we will be processing. Okay, so this is just to show that for a small source here, so it peaks in the center and it fades very quickly. It's a small Gaussian source style. If we now go to the axis of distance in between the two interferometers, we are sensitive to small sources up to large distances, okay? If our source, on the other hand, is very extended, very big source, we are only sensitive to our source when the interferometers are very close, okay? So when ALMA is in the most compact array configuration, we are sensitive to very big sources in the sky. But if we expand the array, we will only be able to detect very small sources and nothing else. We are missing the information from the large structure. So this, you will need to take this into account when you look into your images. You are losing the information of the largest structures. So many people are only worried when they ask for ALMA time. They are really crazy to get very high resolution. So they are like, oh yes, I want the most extended ALMA configuration because I want to reach the milliarc second, whatever, the maximum resolution I want. But usually they don't think about the fact that when you choose that resolution, that configuration, you are not sensitive anymore to the largest structures. So perhaps you are interested in a certain target that has different components, like a very compact central source and then diffuse emission. If you choose a very extended array, you cannot detect the diffuse emission. You have a limit in your in the largest angular scale you can resolve. It's gone. And the same, that previous example, I would like to, so you see, perhaps this one here will be already good. Okay. So if you have, we had that big source, okay? We have the slits, the holes in our filter, basically, and we have the result here. So we saw that our limit is lambda over d, okay? So we are able, let's say that this source is already lambda over d. Oh, thank you. So that will be our maximum that we can resolve. And in the example I show you here, is that sources that are larger than this, we will not go through. We'll miss them. So on the other side, we will only detect sources like this or even smaller. So we have a range. Yeah. And the smallest and the largest size that we can determine comes defined by this distance. And what if, as I mentioned, what if those small sources are on top of a much more diffuse structure? You will not see that, okay? This is what we call in interferometry the missing short space problem. Because you can make this distance as small as possible, putting the antennas as close as possible in order to retrieve the largest scale structure. But at some point, there is a limit in how close the antennas can be, right? So then you think about it, okay, so the largest, perhaps the best way to detect this large scale structure is with a single antenna. Because if I make this distance 0, right, then I can detect the maximum of it. So that's when it comes into play, the combination of interferometer data with single dish data. So with interferometer, you are sensitive to just certain scales. And perhaps you are not seeing the background, right? So you have like a supernova on top of a very diffuse medium, and you want to resolve the supernova, you will not be able to catch the information from the background. So perhaps you want to combine single dish with interferometer data to compensate for this missing short spaces. Okay? So I hope, did you understand? Was it clear? Okay. Yeah.
I understand that, but the diagrams that we're showing again. The diagrams that we're showing again, I believe they will be.
Yeah, you will get it. You mean this?
Those pictures.
Yeah. It's when when you are thinking on they are Fourier pairs. So you are usually you usually have a signal in you have a signal in time, and you usually make the Fourier transform in frequency, right? So what I mean is that if you have like your signal is in time is like this, and you will have your sinusoid, your response in frequency. These axes you are used to them because one is time and the other is frequency. I'm just saying that these are Fourier pairs as well, but instead of time, we are having x and u. X is in the source axis, right? And u is just, instead of taking into account the source axis, we are using the distance in between these two. This is u, in between these two interferometers. So you are, the holes, the distance in between the holes. You have to think of that. I don't know if I made it clear. You change your your reference axis. Instead of being in the source axis, you move to the axis that measures the distance in between the two.
So is you like the path length difference in parts from
the path? Yeah, kind of.
The path length from the start of thinking,
Yeah.
So I guess in that case, the X microphone would be the wave spectrum, but in this case, the stable structure in the sky.
X is the actual structure in the sky?
X is the spatial structure of the
Yes,
sky.
yeah. Mm-hmm. Yeah.
So you're looking at interference at each point, which is separate. Interference at each point you're looking at zero.
The interference? Sorry, I can. No, go ahead. You were.
I feel like I understand microphotometers, even though I don't understand this very much. So in that case, microphotometer, the path difference is just two path difference.
Mm-hmm.
In this case, the path difference is the distance and length path to the object. And each point on the object is a different path
length, yeah. Mm-hmm.
So it's kind of like a bunch of microphotometers all at once.
A bunch of interferometers all at once.
That's not what I get from those.
From there.
What you're calling X is like the angle that sends the
Yes.
thing that we're watching.
Yeah.
We're observing.
Yeah.
So
And then the baseline length is.
This is the dishes.
Yes. So the closest the dishes are, so if the dishes are located very nearby or as they move farther away, we are able to detect the source because it's a small source, okay? But when the source is extended, then you are only sensitive when the baselines, the distance in between the two, Yes?
Yeah,
Okay.
I mean, it's very clear for
Yeah.
me. But what I don't understand is why are there
Oh yeah, you will see it later. Yeah, it's just you will see why are we working on this Fourier space. It's similar to what you will. This is just to.
I guess you could take to it, and like move them apart in trucks while observing the object. They'll give you this path difference, this functional distance.
Mm-hmm.
You can't really just have a fixed set of numbers, a fixed set of buttons or something.
What's going to happen is that we will be working in the Fourier space because we will be measuring what we can measure from an interferometer is the distance in between two antennas and the voltages in those antennas. We can measure that at every time step. This is the information that we get. And what we're going to do is to do an invert of the Fourier transform to retrieve how was the original source there that went through this interferometer, okay? So this is what's going to happen. That's why we are talking about Fourier pairs, because this is what we are going to measure with our interferometer, and we would like to invert to how was the source in the sky. Okay?
But you're going to explain why they are...
Yeah. You will see, yeah. Oh, no.
I understand what we're going to do. I just want to know why we're going to do it.
Yeah. Because it's the way we can, you will see it. Okay.
Thanks. Sorry.
But no, it's good. I like that you stop me and you ask. Yeah, this sentence is the killer, right? So that's why we're going to see later. So forget about it. So they are Fourier pairs, and we will be working in this space. And that was just for you to understand what's the information that we are going to lose when we have an interferometer. We are not sensitive to larger scales, and we have the resolution, which is determined by the distance in the antennas. Okay, so this is a break for reminding a bit, the properties of Fourier transform. To be honest, I inherited these slides, and I don't know who is this guy. So if you know, I will write Bernard an email asking, sorry. His face has been in several slides already, and I didn't have the time to. I assume Fourier is that guy there, but I don't know. So you have to edit this part of the video and cut it out. Okay, so we are going to this slide just to remind you the properties of the Fourier transform, and it's expressed in time and frequency and one dimension. Because with ALMA, we are actually working in 2 dimensions, so we will be doing 2D Fourier transform, okay? It's okay, no, it's going to be easy, no, don't be scared. But yeah, so this is the classical definition that I guess you have seen already in your courses, that we go from time to frequency and the reverse. So we apply the inversion properties of Fourier transform. And then the other important thing is when you have a convolution, a filter, when you go to the Fourier space, it's a product, okay? So that makes things very easy. And this is important for us because we will be, so basically the interferometers, the antennas, what we do is we record voltages at every antenna, and then we send it to a correlator. Correlator is a super computer, which basically, whatever, it's okay. We record the voltages in the antennas, and we send that to a correlator. And that correlator is just making these products in the Fourier space, okay? So it's going to be just, we will be using the properties of the Fourier transform that once you are in the Fourier space, it's just products. Tell me. It's okay. No, now I was just explaining something that doesn't need, no problem. For the video. Okay. Yes. So we will have our signal in the source space. That's what we want to recover, but we will be working in this space. So we will just making simple operations. We are not going to make integrals all the time. So the computers, the supercomputer, the correlator is just making products. And that's what is delivered to us. And then we have to deconvolve to get the original source information. And you will see in a minute why are they. Okay, so this is just to briefly remind you to jump from one space to the other. These are one-dimensional Fourier pairs. So if you have okay, here they show you, yeah, if you have a single source, of course, in the Fourier space, you are working with amplitudes and phases, right? You have you will have 2D information. But if you have a single pulse in the center with a brightness, constant brightness, you will recover just this transform. So here we are already we have the same axis, the angle and the baseline length. Okay, the farther they separate, if you have them two, the farther they separate, the interference changes. This is just a review of what I just showed you. And we will go later to the 2D Fourier pairs, which is basically what we are interested in. Tell me.
Sorry to interrupt.
Yeah, no, it's okay.
Just like technicalities. Aren't there some variables that are missing from those transforms? Like,
Here on the other side, you just. Sorry.
Is there like a T missing or something?
Ah.
And on the
The
inverse
F.
transform, there's also something missing because the left-handed function is T, and there's no T on the right-handed.
Yeah, it's missing a T here, right?
I think so.
Yeah, you are right. Oh.
Here it's a T, and the S is supposed to be a B.
Yeah, you are right. Hmm. Yeah. Oh, okay. Oops. El nu. You mean here you are missing?
That nu
Yeah.
is a T?
No, no.
Hace falta una T nu con T.
Nu T.
It's nu times T.
In the E11. Yeah. I think so. Yeah. But you are right.
Down, how would it be?
Wait.
That's the same with that.
Yeah, it's the same formula there, right? You are missing a T in the exponent. F.
Those are just technicalities. Like,
Yeah. I will look. Yeah, I will look for them because I think you are right that we are missing a T in the exponent, right?
Yeah, but it's okay. Like we know what it means. So.
Yeah. But you are right because then, yeah, it goes in the exponent as well. I think. Yeah. Okay. No, it's okay. Yeah, these are other pairs that you will have to, you will get familiar with when we play with the apps in Sim, because basically it's just to give you the idea that when you have sharp edges, sharp filters, then the response in the Fourier space has a lot of wiggles, and then smooth things give, when you transform them, they also give you a smooth something. So it's very important, it will be very important for the imaging part. When we make images, we will make a lot of use of the fact that the Fourier transform of a Gaussian is also a Gaussian of different width, but a Gaussian is transformed into a Gaussian and back. So this is what we are going to use all the time when we make images. Okay? And if you have, I filter like that, like sharp edges, then you have a lot of wiggles, and this is something that you don't want. So it's quite an...
Like any sharp images like that?
No, it's not the images. It's if you have a filter that you convolve your signal with just something like that. Yeah. It's not that you have a source like this, but yeah. Okay, and this is, yeah, what I just mentioned, right? That if you have a Gaussian in the source space, when you do the Fourier transform, it becomes another Gaussian. And a narrow Gaussian in the transform space becomes a wide Gaussian, and the other way around. This is what we were talking about before, right? So in the source space, you have a narrow Gaussian. It becomes, in baseline space, a wide Gaussian, and the reverse. So, okay. So now comes the funny part, because now we did this in 1D, but ALMA is it's a 2D interferometer. So we also need to train our eye to two-dimensional Fourier transform. Okay, so a delta function, just imagine, it's not a real case, of course, but you have which is a delta in the sky. When you, the corresponding amplitude in the visibility space is just a constant, okay? If you have a Gaussian, a very small source in the sky, when you do the Fourier transform, it becomes a wider Gaussian. Yeah, you have elliptical Gaussians. Why not? Also, when you transform them, still they are something smooth and Gaussian. And here is an example of what will happen if you have a sharp disk, as you were saying. Like, it's not in the sky, but, right? Its Fourier transform will be something with a lot of, I don't know if you see it, like the response in the Fourier space will be very nasty. You don't want that. Okay. In the previous plots, I was just showing the amplitude, but when we do the Fourier transform, we are working with complex numbers, so we have both amplitude and phases. So the antennas will be, we will be recording both amplitudes and phases. We have two types of information. Here is to show you that the phases will give us information on where is the source located in the sky, okay? The amplitude tells you about the intensity, and the phases tells you about the location. So if we have the same case as before, a small Gaussian source in the center, this is what you will get in the Fourier space in the amplitude, and the phases are just 0, okay? Ideally, a point source in the sky, when you do the Fourier transform, it just gives you constant amplitude and 0 phases. If it's located in the center, this is what you get. And this is important because we will use it. This is used for calibration. You calibrate the array. And for that, what we do is we observe sources that are point source-like at the center of the image. So we observe them with the telescope, and then we say, okay, if that source is a point source, it should have a constant amplitude and 0 phase. So we try to fit the response of the array to that. So you need to, to kind of have this dual thinking. So the amplitudes tells you about the brightness, and the phases where it is located. Yeah, and this is just, again, to summarize that when we are working in the visibility space, the Fourier transform space, the amplitude and the phases tell us both things that we are interested in the original source, right? Is everything okay? You look already... What do you think, Alan? Yes, okay.
It's not clear to me why the phase tells where the component is located. Repeat that.
Why?
The phase tells where the component is located.
Perhaps I will show you later a diagram.
For me, it's clear that
Sorry, that?
It is.
Yeah, the how much, but the where.
But I don't see why place.
Yeah, I think perhaps in the 1D, do we have a case? I think it's, I mean, yeah, you have to kind of play with the Fourier transform of it, but we can do it with 1D case.
That's a property of operation.
Yeah.
When you digit a function in
There,
the space, it's equivalent to do a product to the place.
mm-hmm. When you do in the Fourier space, yeah.
If you change the function, it's the same as the product in the exponential.
A a la phase.
Yeah.
Yeah.
So that's basically those phases where space are give information
In the other side.
to other space. It's a property of Fourier transform, or one of the theorems.
I mean, I guess also if you have a perfectly symmetric object in the center, you have an even function necessarily consistent. So you're going to only have cosine part of Fourier transform, no phases whatsoever. As soon as you have something asymmetry, you have to even
It creates a
length scale, so that you should change length scale to length scale. Makes sense.
Yeah, I think comes from the from the formula itself. Okay, so yeah, this is you will play with the absent sim thingy. You will put a source model in the software, and then you will play and see what happens in the Fourier space. Okay. I think, yeah, this is just to go back to the interferometer again. So, yeah, we have, of course, in between two antennas, we have the wave that comes to us. Oh, yeah, this is also very important, I forgot to mention. Because we assume that the sources are very far away, we can assume that the wave that comes to us is planar, right? So you don't have, you are assuming that the wave is planar and then your array is also in a plane. Otherwise, you will have a 3D Fourier transform. Good luck with that. This is what VLBI people do. Because for VLBI, you have the Earth, and of course you have a curvature. So then you have your array is not in 2D because you are measuring, remember, the baselines. So when you have the curvature of the Earth, you have a third component there. So that's why VLBI is very tricky. So okay, what do we do? So the wave comes, it's planar, and yeah, we are using that. So the fact that the wave is coming, it will create a delay. So it will arrive to this antenna, and then a bit later to the other one, okay? So we are recording the voltages in pairs of antennas, and then we are making use of this time delay to do the calculations in the correlator. Okay, this is just for two antennas, but then, of course, the fun thing is that we have much more. So you make all the time correlations of pairs of antennas, and the larger your number of antennas you have, the more information you are recording from the source that was up there. Okay? So I think this slide is going to perhaps answer your question about why is the Fourier transform of the... Okay, so this is what are we going to work on. We have the image plane where the source is with the brightness that I talked you in the sky brightness that I talked you this morning in X and Y coordinates. Okay, so we are working in the visibility space. We have our two antennas, and the coordinates of this, the baseline in between these antennas is measuring the UV coordinates. So we are measuring visibilities, which are the Fourier transform of the sky brightness. Okay. Our work will be to recover from these measurements the sky brightness. So, yeah, I hope it's clear. Okay, so now we are going to build an interferometer. You will see an example of how does it work as soon as we are adding more and more antennas to our game. Okay, let's assume we have, let's assume we have a point source in the sky. So remember, it's going to be, which case? Kind of a very far away object, right? A single point source. So we are going to look to see what's the case when we have just two antennas and a point source up there. So we will be measuring. Okay. We are working in the visibility space. Okay, this is the distance in between two antennas, and we will be measuring voltages here. So this is what we call the UV plane, which is basically measuring the distance in between the elements of our interferometer. So now we only have two interferometers and a point source. So that's the information that we can retrieve. So we basically see nothing, but we have some pattern, and our job is to try to, to recover as much of the information as possible. So with only two, this is what we get. If we add another one to our array, now we have 3 telescopes, 3 baselines. So we have information in 3 baselines. This is our points here, okay? And this is what we recover. So it doesn't really look like a point source, right? But okay. Let's try to add another antenna. So now we have 4. Obviously, the number of baselines is n multiplied by n minus 1 divided by 2. So adding one more antenna to our array is really going to make a difference in the baselines that we have. This would be like the map that you would get from a point source of brightness 1. It's just a simple.
That's the transport. That's
yes, the image, the invert of the, So if we add another one, okay, this is what the pattern we have. We have 10 baselines now, so kind of, it's already starting to show like there is something bright at the center, but because I'm having this, you can imagine as like the wave comes from the sky, and you have a paper made of holes. So what's going to be on the other side is not like the point source, right? It's going to be a resulting pattern of the interference of all these holes that you are making. If you add another one, you have already 15 baselines, so starting to be, you will see it better in the slides when you get them. So I think, yeah, because I think it's not very clear here, but yeah, you will see it better when you see it in the screen, in your own screen. So 7 telescopes is already 21 baselines. We can keep adding, and now is when really we make a difference, because this is for an instant of time. So this was what we will be collecting for a point source if we had 8 antennas, just like that. But now we will not observe it just for 1 millisecond. We will be observing for a certain time. And during that time, the Earth will rotate. Okay, so this is going to give us information on much more spaces in that Fourier transform. So we will be able to retrieve more information from our source. So now we are making the Earth rotate, and we see that we are covering, right? The ideal case would be of a full dish, of a single dish this size, right? But instead of having a dish of this size, we are having just holes here and there that are filling that space as the Earth rotates. Okay? So we are kind of making a fake big single dish covering this UV space. And as soon as you have a good sampling of this space, UV space, then you will be able to recover your original source up there. I hope that's kind of an intuitive idea. How does this work? So this is what we are going to do. So no, we are not going to rotate the Earth, but you will be using this UV data that radio astronomers talk about. Oh yeah, the UV plane, the visibilities. What are the visibilities are? Okay, visibilities is just your interferometer at a certain time in a certain place is recorded in voltages, and that is making you work as a big single dish. If you are not recovering this dish very well, let's say we were aiming to observe 2 hours, okay? And then in order to recover this source, and let's say we couldn't observe such a long time, then of course you will pay for that when you try to reconstruct your image. So your resolution will be determined by this recovering of the sampling of this space. Okay. Okay. So I think, yeah.
So all the observations with radio have to be of the order of 1 hour? Or
No, it depends. It depends. It depends. Okay.
In order to have this,
Yes, you need. Of course, it depends on the source that you want to observe, so how bright it is, and okay, let's say it this way. You need observing time in order to low down the noise. So the more you observe, you will kill the noise. But then you also need time to sample that that space. If you cannot manage to sample all this space, you will also have an output image, but then your resolution will pay for that. And perhaps you will only be able to have high resolution your resolution will not be circular, but ellipsoidal. So you will pay for that. I will try to explain it, a bit better. So you need the two things. You need the time will be determined by a good coverage of the UV plane, and also depending on the brightness of your source, how long you will need to really observe it. It's a compromise in between the two. If you just had a single dish, then you don't need to sample this space. So then you only, the time, observing time will be determined by how strong is your source, okay? But with an interferometer, you also need a good UV coverage. That's what we say. We would like to have a good UV coverage.
What about the redshift when sources are far away?
How does, what do you mean? How does this affect your
measurement?
yes, so, okay. If the source, depending on, what you want to observe. If you want to observe, I guess you are going to, are you thinking about the Doppler shift of a line, for instance? Yes. So let's assume you have a source which is very nearby, and you are trying to detect, for instance, the H1 that I was talking about. So, okay, the atom of hydrogen has a transition which gives a photon out at 21 centimeter. Okay, it's just at a rest frequency, it's at 21 centimeter, not exactly, but very, very close. Okay, so if you are at the if you are at the rest frequency, you have that emission, and you can tune your telescope to that frequency to receive those photons. Okay, if that source is farther away in redshift, then you will have that signal is going also to move in your frequency range. You will have a Doppler effect. So those photons will arrive to you redshifted with respect to that 21 centimeter frequency. I'm not sure if I'm answering your question well. Let's say, for instance, the galaxies that I was showing at the beginning, they are like 1,000 kilometers per second far from us. So they are traveling at 1,000 kilometers per second. Okay, so the H1 atoms that are there are emitting photons that are traveling at 1,000 kilometers per second with respect to us. So we will receive that signal will be shifted in our frequency space by 1,000 kilometers per second. So we need to tune our receivers to account for that shift.
Is it true that all the formulas you've shown us have to do with just one frequency?
Yeah. This is just
frequencies, the spectrum as well as the map.
Yeah. So, what do you mean the formulas I have shown you?
So all percent results apply to one frequency.
Yeah. This would be like a yes. This is just if you were just considering a slice in the frequency space. Yeah. You can. ALMA has many frequencies, so you can make that image for every single frequency that ALMA is measuring, or you can average all those frequencies together.
I have a question about if you can go back to the slide with few attempts. The few is as possible. Yes.
Like this?
Few basic time. Okay, this is just two attempts. So we
Yeah.
have just two dots. Three antennas. Why do you have all these dots?
6 baselines.
There are three baselines, but I can see six dots. So why there are 6 dots?
Oh, well, when you have to, you are, the UV is the distance in between,
Two
yes,
right?
with respect to, one to the other, yeah.
Okay, so if you have 3 antennas, so we have 6 dots. Okay.
Yeah.
And if
Yeah, it jumps to 4 antennas. The double.
You have 4 antennas. You have how many? Yes.
6 baselines, 12 dots.
How many?
12.
Well, okay. Okay. And the other question is if the reason why the dots change in position in the UV plane is because of the fact.
You mean this?
Yes.
Yeah.
Yes. This is because the source is going down or going up in the sky. So.
You are pointing to the source all the time.
Right.
And then the Earth is rotating.
Okay, they are moving in
Yes.
Yes.
You can call it, yeah.
Okay. Right.
This is what's causing, yeah.
Both motion.
Yeah.
So
It depends if you are at the source, what do you see, or if you are in the, yeah.
Right, but it's not just the direction, it's not just the rotation of the Earth, but also the elevation of the source. Because what changes is that's my question. But actually the distance between the antennas doesn't change.
No, it's all the time. It's yeah. You are in that reference system. The distance in between the antennas doesn't change.
So
they move.
What is changing is the distance between the beams coming to the antennas, right? This is my question is actually if we go back, I want to know exactly how these U and V are defined.
Yeah, this is a well, okay.
I don't want to go back to the beginning of the times, but how do you define U and V? Please explain the concept.
Yes. So here you have the example of 2 antennas. So I think it's telling you, okay. I'm gonna try to put it this way. So
I will change my question.
Yes.
U and V are not coordinates or the surface of the Earth.
No, U and V is the coordinates of the distance in between antennas.
Projected towards the source.
Yeah, if you are at the source.
Right.
How do you see? Yeah, you are at the source, and then you and then the Earth
Goes up, and the array
moves with us. Yeah.
Changing distance between them. The distance between them changes.
The actual distance
Does not change.
but the distance
From
the source.
Yeah. If you are, you should look it from the source.
Also, because the source is asymmetric, rotating also gives you information in terms of phasing.
Okay, I hope we made it clear. If not, we can go back again. It's not a problem because we will be playing with this exact thing in the lab. Okay. So yeah, we will be able to rotate the Earth and actually put in and out antennas and see what's the result.
I don't understand why the sense and the capital is being very much the B is the rate.
Sorry, you don't understand?
In the next sense, D from B is the diameter. Yes.
Yes.
But in the image, B is the rate. Why?
Oh, you mean? But I think. So you're talking about this?
They say B is the diameter, but in the image, B is the rate.
B is the radio. B.
It seems like B
Yeah.
Yes.
Yeah. So it's telling you
But
of the lambda over d that we were talking about, the resolution that we were.
In the video, B is defined as the distance from the center to the edge of the.
Ah, you mean this?
Yeah, B is from.
Ah, you mean, okay, yeah, perhaps. But you have, no, because it's the UV definition, so yeah, I know what you mean. When we had sorry, back to the UV definition, we will need to work on that. I thought it would be much more natural. But you had two, the distance in between two telescopes is B, and you have 2 points here, okay? So the size is D, not, do you see it now? Okay. So you have the positive and the negative in the UV plane. So that's why.
Those always produce the same intensity, so they're really the same.
Yeah, it's like, yeah. Okay, we will play this again, but with the software. But it's just to show you another example of how would be the UV plane covered by another type of interferometer. So this one it's the BLA, which has a Y shape, and then as the Earth rotates, you feel the UV plane this way. So it depends on the configuration, on how is the array that you will recover the UV plane differently. Okay? Yeah. So what we have just seen in the example before is how would the telescope respond to a point source. So this is what we called the dirty beam of the telescope. It's basically, in the case of a point source, what you will be able to recover when you image. So it's your limiting resolution. Okay? In our case, because we had many antennas and we had a long observing time and a very nice UV coverage, we are able to resolve a point source of this size. So this is your resolution beam. You are not able to resolve anything smaller than that, right? Anything smaller than that will be broadened to this resolution. You cannot make it better than that. So the image of the dirty beam, it's telling you how good are your observations in resolving. So it's like your CCD cell, right, resolution.
We still have
Another question.
complaints.
Oh, complaints.
Complaints about the number of the dots in the UV plane.
Not
Yeah.
complaints, but doubts.
So let's go back yes to the
We hopefully will make it together.
simplest one.
The
It's
two.
antennas. So
I think one arrow shows from A to B.
And the other is from B to A.
So the whole radius is actually it's the only
Yeah.
quadrant point I think really shows information. So that's why
Half of the, yeah.
No, I didn't.
Okay,
So we have two antennas.
yes. And then you have the measurement from one to the other, and then for the other. So that's why one is called minus B and the other is B.
So why do they plot the both?
I guess,
What we're discussing is the next slide.
yeah,
There are 3 telescopes.
6.
There are 6
yeah,
points. What do the 6 points mean?
because there are three edges of the triangle.
Okay, imagine that you have your reference antenna, because, yeah, you choose one antenna.
They're doing with people.
You are.
So at least they
Yes, okay. You are the.
Three antennas.
We are three antennas,
We are
but
three
we
antennas.
can start with two. Yeah.
Oh, we're gonna start with two. Okay,
Yeah.
okay.
So we are in that case, right? So the distance from you to this is b,
Yeah.
and this is minus b.
Yeah.
So that's why they put two plots, 2 points,
Okay, good.
and then we make the other one.
But there are 2 points. There are 2 points in that picture, which represent both antennas, right? No.
UV
The point
distance.
does not represent the antenna. The points represent the baseline. But it says one baseline.
But if the information is redundant, you have a baseline in either direction,
Yeah.
but actually only one baseline.
It's one baseline, but yeah, you make
There
that
are
representation.
2 baselines, but there's actually just one because they're the same.
Yeah. It does make a nicer graph when you have them all.
Yeah.
So with 3 telescopes, so the 3 of us.
Yes.
So 1, 2, 3, 4, 5, 6. So why are there 6 points? And aren't those both baselines the same as in the past one? But why are they the same in the past one and not in this one?
They are not. Okay. Tell it.
You want to measure something physical, so it's real, and when you do the transform of a real variable, I mean a real function, and it has the property that minus the argument, it's equivalent, it's equal to the complete. So when you that's the meaning of that is know the value of one point, you also know the value of the complex complete. It's just
Yeah.
that's
Very good.
fast.
I guess that's why they made the plots. They don't only plot this one, but immediately they also plot this one because that will, yeah, you are having that information and then visualizing it this way, it gives you a more natural result on the Fourier transform.
But if
what is the axis of this plot?
what would we
You.
make?
Yeah, that's the
But if
baseline length.
If
Yeah,
the
here it's
number of,
yeah.
the number of points represents the number of baselines, and there's 6 points in the graph.
There are 3 baselines, 6 points because yeah, what he explained. It's okay. We will make it. No, it's okay. Yeah. That's good.
Only one number.
Okay, clearly I didn't prepare well for. No, it's good. I like that. No, it's very good. Okay. Yeah, that would be the UV coverage of a BLA observation. Okay.
Thank you. Sorry about that.
No, it's good. You're welcome. So that's why I was trying to explain that that exercise that we made, just imagining that we are having a point source and how would the telescope respond to it, is what we call the dirty beam, which is telling you how well can you resolve things that are in the sky. Okay. So yeah, you don't see it very clearly, but perhaps you can see, guys, that, I don't know. Yeah, there is a pattern. So because the UV coverage, the way the telescope is aligned and the rotation. Okay. So it's really, depending on your UV coverage, you will have some extra noise there, right? So you will inherit a pattern depending on how the telescope is aligned and how long have you been observing. So this is what we call the dirty beam. And yes, I was mentioning if by chance you were trying to observe for an hour to get this UV coverage, for being able to solve such structures. And then it happened to me that when I was observing with the VLA, there was a thunderstorm, and my observations were, well, they had to cancel. So I just had half of the time. So my beam was not circular, was kind of elongated, because I only got good coverage from one part of it, and the Fourier transform of it was, so the image was distorted. So I was more sensitive to structures that go in one direction than in the others, because I didn't manage to get enough time to cover all of it. So yeah, this also is related to what you were asking. It's important to observe during a certain time to be able to recover a circular beam, or otherwise you will only be able to detect structures to a certain direction better than to the other. Okay, yeah, this is just an example that we will be working with extended sources. So that would be the Fourier transform process by adding more and more antennas when you have a extended source like this. So if you just had the, I guess like the 2, 4, 8 antennas as we did for a point source, this is what would you get when you add more and more baselines. I'm not sure you can, yeah, you will, I will give you the slides, and then tomorrow when we go to the lab and open the absent sim, we'll go through this.
I have a question.
Yeah?
So when you haven't got these moving baselines, this map looks a little bit difficult to interpret.
When you have?
When you have not many baselines,
Yes.
it's difficult to interpret the map.
Yeah.
But because you know exactly what all the baselines are and all of that matters, you actually have more information than what it looks like here. Like, can you, for example, your source could say how big it was, even though you can't remember it.
Yeah.
What information you can obtain because you know a lot about the mathematics of the.
Yeah, that's if you mean you can retrieve more information.
Yeah. Are these pictures worse than they really are? Information, scientific information.
Depends on which information are you trying to talk, like the how bright it is, or how
big it is, whether it's clumpy or smooth.
Yeah, that depends on your on your resolution, on your DRT beam. I'm not sure I'm understanding you well.
Like in some of the early ones you showed adding more and more baselines and the point source appeared.
Yeah.
But if you knew there was a point source,
if you are,
you could look for it even when it wasn't a very good image. You had a model of what it should look like.
Yeah, if you, of course, depending on what you already know from your source, I guess. After all, you are trying to image using kind of a model, right? So this is related. Yeah, we will see it when we do the deconvolution algorithm, because basically it's already behind it. You have infinite solutions that would fit when you invert this process and you go back to the original image. You have infinite images that would fit that Fourier transform, right? And you will have to choose which one. So I think perhaps this is related to what you are saying, hopefully. Okay. I think we will, this is what the software that we will be using, and I don't know what time is it. Para las 12. Ah, okay. So I really go very fast, faster than I thought. The thing is, because I had prepared already to be in the lab, perhaps to do this, but we will do that tomorrow. Shall we perhaps stop and do the?
We stop at 12. Sure. I have a question.
Yeah, we stop at 12.
When you work with telescopes and CCDs, you have these flat beams down and calibrate the sensitivity the surface of the CCD. What happened in this have that the response of different antennas are different, and you cover all the UV plane. If one antenna has a different sensitivity than the other, it will distort.
Yes.
So you have some kind of flat fields.
Yes, that's what. That's yeah. Very good. We have the calibration. Yeah. Yes. So what we do, it's a classical process to calibrate. Basically, you choose an amplitude calibrator. So because you're receiving waves, you have two things that you want to determine: the amplitudes and the phases. Okay. So you use first a short observation on a bright calibrator that looks like a point source. Okay, its Fourier transform will be just flat amplitudes and 0 phases. So you observe that for a short period, let's say 10 minutes, or depending on the sensitivity of the telescope, you observe it for a short time. And you measure it, you measure the amplitudes and the phases of that target, and you make it.
But with each antenna, not with the array. With
all the antennas.
All the antennas with one source.
Yes.
Just 10 minutes.
Yeah, 20 minutes. And you would get something like that we saw. It's just a point source, so, and we observe instead of for 1 hour, just 10 minutes. So you will have just a short UV coverage, but that's okay. Because it's a bright source, it's point source, so we have a model of it. And we know how bright it is. Okay, so we use those 10 minutes to calibrate the amplitudes and phases, so the amplitudes of our antenna response, because we know that source is that bright. So we scale the amplitudes of our antennas, our array, to that. And then we go to the source field, because of usually the amplitude calibrator, it's not necessarily close to our source, okay? And we have we have distortions depending on which area of the sky you are using. Okay, the phases are really different from one part of the sky to the other. So you move to your source place, you observe another calibrator which is perhaps is not so bright, but you will use it as a phase calibrator, assuming that if it's close enough, you are in kind of in the same plane and the phases are the same for your source and your phase calibrator. So in the calibration process, you take the amplitudes of the amplitude calibrator and transfer them to your source. And then take the phases of your phase calibrator and transfer them to your source. And then image. Okay? So that's how you calibrate the amplitudes and the phases.
What is the baseline of the DFT? Is 37 kilometers?
Yeah, it's 27 antennas. No, it depends. Yeah, it depends on the configuration. That was the configuration. The one that I showed, it said 2 kilometers or something like that. But then the A is, I think, it's a more extended. So I'm not sure how far away do they go.
Yeah,
I know they have A, B, C, D configurations, and they change every 3 months from the most compact to the most like this all the time.
I was wondering about the weather, because if you have a long baseline but not too long, you can have one place a little bit different weather.
For example, east and west side of Medellin.
Yes. Yes, the north and south. South is always raining. North is dry.
Yeah, that's true. Yeah, you have to. You might have like, you mean the usually the weather, at least for ALMA, which is very clear, the weather makes your faces noisier. So yes, so that's the weather can be different in different areas of the sky. So you are worrying whether the amplitude calibrator will be affected differently by the weather than your source. That's why you put the phase calibrator nearby. Okay. The amplitude calibrator is very bright, and you will get,
So
yeah.
explain me again what is the phase calibrator. Is that an actual source?
Yeah. It's an actual source. But, okay,
It's different.
it's,
Just needs to be different.
there are not so many well-known sources and very bright in the sky, in the radio wavelengths, okay? So you have like certain targets that are super bright, and just with a very short integration time, which is related to that, you will get a high signal to noise. And this is what you need for calibrating the amplitudes. So you need a short observation of a very bright target that gives you good signal to noise to calibrate the amplitudes. You have many other weak sources that are also kind of point source-like and nearby your target of interest. But they are not as so bright for a short observation to give you high signal to noise. So that's why you first use a very bright source, 10 minutes only, which is point source-like, that can give you the information on the amplitude scale. You take that information and you transfer that scale to your phase calibrator. So you observe the phase calibrator, let's say, depending on the telescope, but for instance, for my VLA observations, it was like 5 minutes, 3C295, which is a very bright source. Then we went to my target field. We observed 5 minutes phase calibrator, 10 minutes source. 5 minutes phase calibrator, 10 minutes source. 5 minutes, because the phases change in time. Because of the weather, for instance, you can have a cloud that goes through, and then your phases have changed. So you take your amplitude calibrator, solve for amplitudes, transfer this to your phase calibrator, solve for the phases, and transfer that to your target. Is that clear? And then, yeah, that's why you are observing just perhaps once at the beginning the amplitude calibrator, and at the end, perhaps you observe it again for the amplitudes. And the phase calibrator, you observe it every now and then, interleaved with your target. Yeah, so yeah, we will see this in the calibration procedure, but.
Bueno. Antes de que se me vaya. So.
Do you want to use
No. Give me the mic. Do you need? Okay. Do you need some time? Oh, okay. Okay. Let me see. Ahí está. Hay audio. Sí, audio. Bueno. Ok, guys. Bueno, muchachos, entonces, Pablo les dijo algunas de las... Bueno. Correcto. Bueno, entonces, muchachos, importante tener en cuenta la página de Moodle, la página que está en astronomía. Yo vi que ya, no sé, a Jorge lo vi por ahí, ya muchos se metieron a la página, pero es importante que estén ahí todos, porque ahí van a estar algunos ejercicios prácticos que van a dejar los profes. La idea es que en este curso, a diferencia del curso, por ejemplo, del año pasado, todo lo evaluemos antes de que ellos se vayan, ¿cierto? Que no quede nada de tarea y que all to be, yes, all the tests and the homeworks to be done before you leave, right? Okay? Yes. So, entonces hay que tener la cuenta allí porque, por ejemplo, for example, Alan has some exercises and he wants that you upload the result or upload an image or a screen capture of the exercise. So, tenemos que tener todos cuentas allí. ¿Listo? Bueno. Mañana tenemos entonces hoy la actividad era aquí. Y va a ser todavía aquí, la de Alan ahorita por la tarde. Pero mañana es en el aula 625. Correcto. Desde las 9 a las 9 comenzamos. A las 9, mañana, tomorrow at 9, we will have the first test, which is yes, a test. It's multiple choice, maybe true and false questions, something really simple, but it depends on the slides we saw today. These slides, these topics that Carmen was, yes, telling us. Yes, no. At 9 o'clock, we will have the first test about the Carmen topic today. And at 2 o'clock, we will have the test.
1 or 2?
One is from
No, but 1 o'clock or 2 o'clock?
2 o'clock. 2 o'clock. 2 o'clock is the afternoon session, right? Right. Okay. The tests are written tests, are done here. But if you cannot come to the class and present the test, we will upload the test to the website. Las presentaciones las subimos ahorita. O sea, esta noche ustedes tienen las presentaciones para que repasen las presentaciones. El video también se sube hoy a YouTube, si quieren volver a ver alguna parte del video. ¿Qué más se me olvida? Ah, bueno. Muy importante. En la página, in the web, in the activity site, activity website, which is the place, I have a poll, yes, estos formularios de Google, para que, por favor, todo el tiempo estén diciendo cómo van las clases. ¿Listo? O sea, le estén evaluando permanentemente. Estoy aburrido, no me gustó, no entendí, definan bien, no se ve la letra. Quéjense de todo porque yo sé que Carmen and Alan want to know what is happening in the class. Sometimes, yes, you just don't say anything and leave. No, we don't want that you leave because you are bored, right? We want you are happy, but okay, working out. Yes, sí, dime. Ah, listo. Pero ya te registraste en la plataforma, ya entraste, Ok, listo. Es muy sencillo, pues, pero sí, yo creo que tengo por ahí un video tutorial. And, no, hay media hora, half an hour at the beginning of the class is maybe 10 or 15 minutes for the tests and 15 minutes to solve the test. Okay. Yes, to see the answers and okay. The last point, así.
Para entrar al curso necesitamos alguna contraseña como por ejemplo con Ameba o...
Sí, para entrar al curso en Moodle hay una contraseña que es AstroTwin-2016, está en el correo. Bueno, creo que eso es. Recuerden que los miércoles no tenemos clase. Este miércoles, pues por obvias razones. Y el miércoles de la semana entrante, porque, bueno, los profesores necesitan una pausa en la semana. Entonces, pero aún así, el próximo miércoles, pues como vamos a estar trabajando mucho en el laboratorio, el próximo miércoles la sala va a estar abierta, los profesores van a estar aquí, entonces la idea es que se aproveche para hacer trabajo. Repito, o sea, el mensaje es que todo lo que vayamos a hacer se haga mientras ellos están aquí. Otra cosa importante, muchachos, la electiva. Esta es una electiva, y como les dije en la reunión si ustedes vinieron a la reunión de estudiantes, la idea es que al final ustedes decidan si quieren que la electiva vaya con la nota que saquen en este curso. Si al final ustedes dicen, no, me fue muy mal, no hice nada, entonces la electiva no va. Entonces, o la pueden matricular en ajustes, pero con la libertad de después removerla de su matrícula, o la pueden no matricular, terminar este curso, la certificación, y el próximo semestre se les pone la nota. Pero entonces, sí piensen en la posibilidad. O sea, yo creo que si ustedes piensan que esto es un curso que se compromete, se dedica más a él. Bueno, ok. ¿Listo? 2 o'clock. See you later.
Los ibas a pegar esto.
Ah, bueno, las iba a pegar abajo.
I'm not sure when you come into your lecture.